Comparte tu pantalla en público. Okay.
Seems like
No,
we're
pero
live,
quieres compartirlo.
I guess.
¿No? Sí, estamos así.
Okay,
Okay.
Papá.
Ay, me muero de risa.
let's get started. Okay, we'll go in English for this one. Thank you all for coming. Good. Okay. So, my name is Santiago. Usually we go by Pala.
I'm Nico. I go by Nico.
We're both engineers at Aztec. Highlight on. Do you want to? ¿Quieres cerrar la puerta? Cool. Important thing: we're engineers. We're not cryptographers. We're not mathematicians. We have no idea what we're talking about. We're here to share an intro. That's what it's going to be. It's going to be very informal, very lightweight. Please interact and ask questions at any point in time. Before we, okay, some more people coming in. Okay, before we begin, massive thank you to someone with whom we would definitely not be able to be here. And that's public education. Okay, let's get started. Okay, we'll start with an overview of what we mean by zero knowledge, what's a snark, what are a couple of the different buzzwords, what this is, and then we'll go into circuits that we develop at Aztec. Then a couple of examples, get familiarized in how NOR works, what kind of circuits, what kind of stuff you can build. Then we'll go a little bit into the Aztec network, which is an offshoot that we're building on Aztec using things from NOR. Okay, let's start with zero knowledge. How do we start with zero knowledge? Okay, so I think the important thing with zero knowledge is understand that zero knowledge proof is meant to convince another party of something, of a computation that you have done. Okay? It has a couple of properties in that it must be complete and sound, otherwise it wouldn't be much interesting. But the important thing is zero knowledge. It's the fact that you are not conveying any more information that is strictly necessary to the recipient of the proof. Most important thing here is we're always talking about at least two different parties, the prover and the verifier. The person who knows something and wants to convince the other one, the verifier, that they know something. A classical example could be where's Waldo?
Where's Waldo? Yeah.
Okay, where's Waldo is a classic example of zero knowledge proof. For instance, everyone familiar with where's Waldo? Like Hawali? Yeah. Okay. Language matters. So, for instance, if I have a picture of where's Waldo and I know where Waldo is and I want to convince him that I know it, but I don't want him to know where Waldo is, I can basically take a piece of paper, cut a little hole in it, place it on top of the paper, and I just place it so that only Waldo is visible. I show him, hey, look, here's Waldo. I know where Waldo is, but he doesn't know where he's in the page. So,
or I could also give you the page, and you could go into a room, destroy the page, but only leave Waldo, and then give Waldo back to me.
that's more interesting because
Yeah.
it involves destroying something.
Yeah,
That's
yeah.
always fun.
And then I know he has it because he shows it to me, but I don't know how he did it.
So that's sort of the high level idea, right? Like, I know something, and I'm going to prove to him that I know it without necessarily sharing what I know. A very simple, very stupid example that we'll go a couple times over is, for instance, even a very, very large number, I know how to factor it. Like, I know two other numbers, and when I multiply them, I get a big number. But I'm not telling him what those numbers are. And I can create a proof that I know that. So far, so good.
Yeah.
That's pretty high level again. So what's a snark? These terms usually go hand in hand, and sometimes they're interchanged, even though they're sort of different things. SNARK stands for Succinct Non-Interactive Argument of Knowledge. Let's unbundle this thing. Succinct means that it's something small. Like when I'm creating a proof, that proof must be small in size. Most importantly, must be very fast to verify. Like succinct es sucinto, corto, chiquito, pequeño, small, basically. Yeah, small. And the idea is that it's small regardless of how much effort you did to complete the proof. For instance, again, going back to the example of I know two numbers and when multiplied, I get another one. Those numbers could be arbitrarily large, but the proof that I'm generating that he needs to verify remains small, regardless of how large the numbers are. And especially like the speed of verification is fast. Like he can verify in very little time. Now, a very important concept, right? Like, it's a proof that doesn't need a game between the two parties. Like in the Waldo example, we're going to okay, I'm going to a room and showing something and coming back to him, he gets back. Like there was sort of a back and forth. In a Snark, we don't have that. Right? It's completely non-interactive. It's a proof that I produce. I can leave it there. I can get it out, and anyone can download that proof and then verify it in no time. Argument of knowledge is no.
Yeah, I'd say that non-interactive is maybe a key property in that most of these schemes require some back and forth and being able to put some data on anybody at any point in time after the fact without my participation, be able to verify the proof is how these things are used. So I also realized this could have been called small, non-interactive argument of knowledge. Like it's like
It
simple.
would actually be nicer.
Unnecessary.
I'm sure some mathematician would be annoyed by that. But... Okay.
Oh, also going to say, note that Snark is not zero knowledge necessarily. A Snark can be an argument of knowledge that is succinct, that is non-interactive. A CK Snark is the one that adds zero knowledge to it. But you can also have all of these properties without having, but also having public information, and that's fine. And there's actually very valid use cases for that.
Yeah. For instance, Snarks, which I'm sure you guys have heard about, which are a variant of Snark if you want to, they have no zero knowledge. Like there is no private information going around it there. Okay, why? Why is this interesting? More in general, like one of the most interesting things about zero knowledge, and with zero knowledge I'm talking about CK and Snarks and all these fun little things, is that this comes as programmable cryptography. What does this mean? This means that if you need to prove something, if you need to generate a scheme, you don't need to hire a bunch of mathematicians and cryptographers, lock them in a room for a year and wait until they come up with someone. You can actually code the kind of thing that you want to prove with cryptography and generate a circuit for it. This is basically us, dumb engineers, now have access to creating new cryptographic primitives. That's the interesting thing about this. Classic example is ring signatures, for instance. Ring signatures allow you to prove that someone belongs to a set, like very, very broadly speaking. That's like a very specific cryptographic scheme. You can either come up with a way like understand how to develop and design and implement the scheme, or you can write a zero knowledge circuit in a couple of lines that does exactly the same and never understand a thing about ring signatures. And you'll be able to do the same. And like this opens the door to a bunch of things, like a classic example being systems interoperability. Like if you have the power of convincing someone else that you have done things according to the rules, that you have performed a certain computation, you can use that to have two systems talk to each other. Like you have two systems that speak different languages. You can send information from one to the other and converting them trustlessly using a Snark. One that's of particular interest of us is, of course, about privacy. Like we can do stuff in private. We can prove that what we did is okay, it's private, it's according to the rules of the system, but not reveal anything. For example, private transfers. Like I can send him a transfer of money, and the only thing I reveal to the world is, hey, something happened. And here's a proof to show that that something was valid and is according to the rules, and I didn't print money out of thin air. That's it. That's the only thing we reveal to the world. And it's a transaction that's completely private between us, yet it impacts a global state, for instance, of a blockchain.
Yeah, maybe to make that sound, when you purchase something with cash, you're also having full privacy. You prove I give him money, and he knows that the transfer happened because I gave him money. He knows that he has the money because he received money. He knows that I got the money. Hopefully, I didn't print the money out of thin air, but so the origin is valid and it came from somewhere. But nobody else knows anything, and he knows that everything's okay, even though he doesn't know anything else about me, and I also don't know anything else about him. Mm-hmm. And that's essentially the exact same trust conditions.
Yeah. And like privacy can be used not just for transfers, like it also is for voting, for participating in the system, like just whatever you want to do. Identity and attestations is also a very interesting one. Like, for instance, for KYC purposes, let's say you need to sign up to a site, and that site needs to verify your age. a classical example is, okay, one option is that you have to send them your passport or something that reveals all your private information, such as your exact date of birth, as well as some entity that attests to that date of birth. Or you can generate a zero knowledge proof that says, hey, I'm over 18, and that's it. Like the input to that proof, like what you're doing is you're generating a proof that says, given this piece of private information, which is my passport, my private information, okay, I'm generating something that can convince anyone that I'm over 18. The last one, probably one of the most interesting ones when it comes to rollups and blockchain, is compressing computation. Like, remember that one of the properties of SNARKs that we discussed was that it's succinct, like it's small, it's very, very fast to verify. That means that we can compress a bunch of computations, a bunch of actions into something that's very, very small to verify. For instance, I can grab all transactions in an Ethereum block, compress them into a SNARK, and just share that SNARK with anyone and say, hey, look, like the result of the transition function, the result of applying all of these transactions in a block in Ethereum over this state is this new state. You know, you can trust me. You don't need to run all those transactions yourself. You can just verify this proof that I'm giving you, and that's it. And the important thing is that there is no private information there, right? Like, we're not talking about zero knowledge anything. We're just talking about SNARKs. We're talking about compressing computation, which is how 99% of the CK rollups work, right? Like, what they do is they compress, they execute all of the transactions that happen on the L2, they derive a new state, and they post that to L1 along with a zero knowledge proof. That says, hey, trust me, I ran the transition function, I've done everything by the book. Here's a very, very quick to verify proof so that we can convince that this is the new state. So that's the main use case for SNARKs in the context of CK rollups.
This is typically a source of confusion, as you'd think that a CK rollup has zero knowledge on it because it's called CK rollup. But actually, as you mentioned, all of the inputs are public. There's no zero knowledge. It just so happens that the SNARK technology, which is typically used for CK SNARKs, also has this nice asymmetry in computation in that proving is very cheap, is very expensive, but verifying is very cheap, which just so happens to be exactly what you want if you were to scale a blockchain. But CK rollups don't actually deal with privacy or zero knowledge itself.
Except for us.
Except for
But we'll get to that in a couple of minutes. But yeah, like, to give an idea, like what would take you to like a set of transactions that will take you a minute, for instance, to execute on top of Ethereum, it will probably take you an hour to generate a proof for that, but then a second to verify that proof. So there's a massive asymmetry between all of these things. Like just executing, it's fast, proving extremely slow, but you only need to prove once, right? But you don't need every single node, every single Ethereum node in the planet to execute the same transactions. If only one of them is good enough to generate the proof, all the others can verify, and that's it. And you don't need to be repeating computations. Are we good so far?
Yeah.
Cool. Okay, buzzwords. As soon as you start scratching the surface of this, you'll find a lot of very, very weird and annoying terms. Before you get annoyed at mathematicians, just let's have some introspection and remember that all of us engineers also love to put weird names on everything. Just start thinking of JavaScript frameworks or whatever new thing comes every month. Okay, same things happen with SNARKs. Like, the thing is, there isn't one way of doing zero-knowledge proofs, of doing SNARKs. There are a lot of different families, a lot of different frameworks, a lot of different proving backends, a lot of different combinations. Like, for instance, the one that we're using at Aztec, correct me if I'm wrong, but I think it's Goblin Galactic Honk with Datables and Poseidon Churn. But isn't that Goblin Galactic? Never mind, you get the idea. The important here is understanding the trade-offs of the different proving systems, right? Something that's very common, especially with old-style proving systems, is there a need for a trusted setup. Trusted setup is sort of a ceremony where a lot of people contribute randomness, and as long as one person within that set is honest, you know that the circuit is going to work as it's supposed to be. Maybe some of you remember like the KCG ceremony for Ethereum a while back. Okay, that was exactly it. The idea is trying to get as many people as possible to contribute with randomness, because one honest actor means that the trusted setup is sound. What's a trusted setup is basically a process by which you generate a bunch of keys that you will need for generating the proofs later. That's pretty much it. Some flavors of proving backends don't need a trusted setup. Others need a trusted setup for each individual circuit you write. Others just need one trusted setup, like for the whole family, which you can download and use with the circuits that you're working with. Other concerns like proving time, how much memory you need for proving. Like Polygon CK VM, I think it requires around 800 gigabytes of RAM for generating the proof, which is okay, it's nice, but you need a pretty beefy server for that.
For example, if you want to submit a proof to the L1 that your L2 is working correctly, then yes, you can get a Giga server on AWS and it's fine. But if you're trying to generate proofs on your phone to make a payment, then you need different compute constraints.
Mm-hmm. This usually have an indirect impact in verification time on proof size. Like you can get proofs that are really, really small, or proofs that are like several kilobytes in size. Other gadgets that you can throw in, like whether the scheme is quantum secure or not, which will become a problem in a couple of years maybe. And recursion cost, like this is sort of a property that some schemes have, that they can be made so that it's very cheap for a circuit to prove itself, which is handy when you have a computation that you iterate over and over again, or something that you want to do recursively. Like a nice example of that one is Mina, which is a blockchain that basically on every block you post a zero knowledge proof, snark, that the tip of the chain is correct. And every block consumes the from the previous block and builds on top of it. So at any point in time, like a light client of Mina is trivial, you basically download the block, you check the zero knowledge proof, and you know that the state root is true. Okay. That's sort of the backend. Like that's the math, let's say, that's going to build your zero knowledge proof. There are a bunch of things intermixed there, but let's call all of that the backend. Then you have the language, like the front end, like what you're actually going to write to create one of the circuits. During this talk, we'll be focusing on Noir, which is a DSL that we built at Aztec with Aramódico Moquito. You get the idea.
Some people build.
Yeah, some smart people built. Circon is probably the most popular one, mostly because it's the one that has been around for the longest time. It's pretty low level, but personally, I would if you want to understand the nuances of writing zero knowledge circuits, because it abstracts very, very little from you. Halo 2 is not a language, but a framework, a library for Rust, which is super low level, but allows you to write very optimized things. Cairo, language from the Starknet people, mostly focused on working on their blockchain. Narc, a Go library from Consensus, and O1.js from the people at Mina. Again, different languages will have different trade-offs in terms of expressiveness, of how easy it is to write, how mature they are, whether they are audited or not, and also which proving backends they support. Some languages support multiple proving backends, others only one. So far, so good?
Yeah.
Okay. Let's go more in depth into what in a circuit. You want to take this one?
Yeah, sure. So when we say circuit is, if you were to think about computers, what you would call a program is called and makes the proof about whatever it is you're trying to do. It sort of looks like a program. We're actually going to see how it's slightly different, but it does have inputs and it does have assertions, which are typical program things. The key things, or rather the two key things, is that inputs are divided between public inputs and private inputs, where private does mean private in the sense of only I know about this. So this is private in the privacy sense, not in the computer parlance. And assertions in the form of I know that a fact is true. So for example, a typical assertion that a circuit may make is there's two inputs, which are private. So I don't know their values. Let's call them X and Y. But I know that these two, when multiplied, produce this thing, which would be a public input to the circuit. So this is a circuit with two private inputs, one public input, and this is the assertion that it makes.
Sorry,
Please, yeah.
is it supposed that the relation between x and y, I mean the computation is known?
Yes.
Okay.
Yeah, this is literally what the circuit
The next one.
the proof. So if you were, say you want to write a program, right, that does x times y. So you have a program with two inputs, an output, does the multiplication, yields a value. So if I wanted to convince you that I know these two values that produce this result, I would have to give you these two values, x and y, then you run your program and you get a value out, which is the one that I gave you. And that's good. You verify that I know the values. But I have to give them to you, unfortunately, which is what we're trying to avoid because we want to have privacy. In a circuit, this would look something like this instead. There's an input, which is private. The x and y inputs are private. Now this thing, what was before the result of the computation, is a third input, which is the circuit, which is what you were asking, performs the computation, the result, and then I build a proof over this. So if I give you a proof and you verify the proof, and you know that, then you will know that I know some value x and some value y, which coupled with that value z, passed this assertion, meaning the circuit executed correctly and no errors were found.
I think that the important thing when working with circuits is always bear in mind that there are two parties. There's the prover and there's the verifier. Unlike in a normal program where there's just the person who runs the program, you have the prover knows the private inputs and the public inputs and generates the proof, and then ships onto the verifier just the proof and the public inputs. The private inputs remain hidden, remain property of just the prover. As in the example that Nico was saying, Z and Y are never sent to the verifier, only Z and the proof.
Yeah, so you may think that, for example, if I want to prove this to him, I would run something like this with the x and y that I know, get this out, and then create a proof for the circuit so that he'd be able to verify the result without knowing what the inputs are.
Okay. So let's go a bit into like what's the flow of working with a circuit, right? Like again, you start by writing the circuit, like writing what are the private inputs, the public inputs, and the assertions, basically the relationships between those inputs that you want to prove. You may need to create a trusted setup, this magical ceremony where you basically end up with a bunch of proving keys and verifying keys that you need to distribute to everyone who wants to work with the circuit.
You can also reuse an existing one, as you mentioned.
Yeah.
You don't necessarily need to do one per circuit.
Depending on the proving pattern, yeah. And you basically ship that to your users. When a user wants to create a proof, usually what happens in most circuits is you have like this dual step. The step, as Nico was saying, where you first execute and you then prove. In the previous example, you would input x and y into the circuit, and you will sort of execute it in a way. And so you get Z, you get all the values. And once you have done that execution, then you actually generate the proof for that. You can think it of like in two different steps, like one step in which the circuit runs, and that's it, and performs all the computations, and another pass where it actually generates the proof over the computations it has done. Otherwise, you would need to basically pre-calculate everything and leave everything to the circuit from scratch. And then what you basically send the proof to someone and they verify it along with the public inputs. Again, this more or less making sense. We'll go into a couple of examples, maybe that will help more. Okay, let's get into some examples in Noir. So we're saying Noir is this, right? It's a language for, it's a language for writing circuits, heavily inspired by Rust in terms of syntax, and it's backend agnostic, means that you can plug different proving backends into it. Like the current one that's hooked in is Plonk, and we're working on a Honk integration. Yes, those are real things.
So going back to that example from before, the circuit that proves x times y equals some number, this is a Noir program that does just that. This is actually an entire Noir program. It doesn't need anything else. Field, it's a finite, it's a number. You don't need to worry about what it is. Field essentially means number, very large number type. So this is a program that receives two inputs. By default, they're all private, so these two values will be private. It outputs a value that is public. So you say, hey, Noir, please run this circuit and produce a proof. You'd feed two values for x and y. It would do the computation and then output a value that will be public. So this is what he was talking about, this dual nature of running the circuit and proving the circuit, Noir makes it so that the thing sort of looks like a program, meaning it does a couple of things and there's some output, but actually these will all be converted into these two being private inputs and this being a public input into the proof that you then verify. That was a sort of toy example, but say you want to do something a bit more intense. If we were to, on a blockchain, say on Ethereum today, you can prove that a value is part of a set, assuming you have something like a Merkle tree and the contract knows about some Merkle root. So the way you do that, which is something that most systems do today, is there will be a function. You say, hey, I want to prove that this value exists on the tree, and here's some data, the actual Merkle path, so you can actually you can assist the program to prove that this fact is correct. So you'd process the entire proof and you'd say, okay, yeah, the root that I got is the actual root of the system. That's great. And you can also have the contract check some properties, such as this part of whatever thing you pass to me fulfills a condition. So in this case, you're passing some balance of a user, and you're also showing that the thing that exists in the data set, the balance of that user, is larger than some value.
Sorry, before we go ahead, everyone knows how a Merkle tree works? Yeah, no, more or less. Quick refresher. Okay. Oh yeah. You want to do it?
No.
Okay. Okay.
I dislike Merkle trees.
You will be fired if I hear.
Yeah.
Okay. So Merkle tree is a binary tree. Okay. Like every node has two kids. Pretty vanilla. And the main property of a Merkle tree is that every node is computed as the hash of its two children, okay? So let's say I get a value A here and the value B in there. These are called the leaves of the tree, like the lowest bottom. You hash them together and you get this value. To get this value, you hash these two together and so forth and so forth. At the very top, you get what it's called like the root of the Merkle tree. The nice property about Merkle trees is that by sharing, if everyone agrees on the root in a way is a hash of every single element in the tree, right? So the root acts as a commitment to every single item that's on the tree. If later I want to prove that the given value is on the tree, what I need to provide is called the sibling path. It's like the set of elements that are adjacent, that are the siblings of every element as I go up the way.
So given this value, I'll provide this, this, and this. With these two, I can compute this one. With these two, I can compute this one. With these two, I can compute this one. And then I can verify that the root is correct. And because of magical hash properties, I would only be able to do that if the thing is actually correct and I actually know the values and the tree is actually the same due to no hash collisions.
So whenever we talk about a Merkle proof, it basically means a set of values along the tree that allow me to prove that the given element is present on the tree. You can do some tweaks to a tree in order to also be able to prove non-membership, like proving that the given element doesn't exist on the tree. It's a bit more complex, but it's also doable.
So essentially what is happening here is these are balances. So here there's a user under balance. Presumably there will be multiple users. We all agree on a root, meaning we agree on the set of users and balances. And what I'm doing is I'm showing that this concrete user with this concrete balance is on the tree by showing this value and showing this ones as the path, and then the thing computes the thing, and we're all happy. And in this case, we're also proving, just because we can, that the value in this node is larger than some minimum value. This is how there's plenty of blockchain applications today that rely on this sort of thing. But it should be noted that when doing this, we are revealing the entirety of this thing. So, for example, here we cared about the value, but not the address of the user, but we have to show it in order to actually compute the entire hash. And we also have to show all of these elements in order for the thing to actually compute the proof. So in that sense, you may say that we are showing more information to the public than we strictly require, depending on what it is we're trying to achieve. So if you wanted to do the same thing in Noir, yes. So this is, again, an actual Noir program that does exactly that. Very Rust-like. The import syntax is the same. You have structs. This looks like a program, even though it's a circuit. And it looks like this is something that you'd execute. That is, again, because of the dual nature, you execute this to generate a proof, and then somebody verifies that proof. So the interesting thing that I want to point out here is, if you look at the signature of the function, and more importantly, which values are public and which are private, here, well, this should actually be private. Imagine it doesn't say public. So we'd have the minimum value would be public, everything else would be private, and then this result, which is the root of the tree, is public. So what I'm doing here is I'm saying, hey, I know that in this tree, which is public, so it's the exact same root you have, there exists some value somewhere. I'm not showing you the path, and I'm not showing you the user, and I'm not even showing you the balance. All that I'm showing you is that the balance is larger than some value that you may wish, but I'm not giving you any other information. So yeah, you could presumably do that to like the sort of things that Pada was talking about, such as showing, hey, I exist in this set and my age is larger than 18, or I don't know, I have X many POAPs, therefore I should be eligible for some discount. You don't know which POAPs, you don't know who I am, you don't know anything else about me, but you do know that those things are true.
Yeah. Like something worth mentioning is that Merkle trees also power Ethereum itself. So this allows you to perform zero knowledge proofs over Ethereum state. So you can actually say, like, in this given contract, there is an entry with an address I control and has this set of properties. Like, I have at least this much amount in DAI. Or as Nico was saying, I have at least 2 POAPs for DevCons. I'm not going to tell you which ones, and I'm not even going to tell you who I am. I'm just going to tell you that I have control of that address. A circuit like that would have as private inputs, I don't know, my private key or a signature over whatever I want to say. But again, it would be a private input, would be something where I'm just proving to the circuit, hey, I have control over these addresses. But I'm not revealing publicly which those are. Like, all I'm saying is that I control them. And also within a set, which is Ethereum state, like there are entries related to the address that are POAPs, and they are the ones we're interested in. So, a couple of things you can build with Noir that people have been building actually. A nice example is Battleships, which is a battleships version of Batalla Naval. Nice thing about this is, like, in Batalla Naval, battleships, like I told him A6, he tells me miss, and I have no way of confirming whether he's telling me the truth or not until the very end, until we finish the game, where I have to check that, well, he didn't lie. With this, he can actually give me back a zero knowledge proof saying, hey, it was actually a miss. Like, given a commitment to his board that he shares in advance, he can actually create a proof saying, for this commitment to the board, think of it as a root, as a Merkle root of his entire board, A6 is water. And that's the only information he gives me. That's only everything I see as a verifier here. And I'm convinced that he's not lying, but he's not revealing any information about his board. Like, again, applications general in games like are massive.
Yeah, it may be obvious, but like, this is what zero knowledge means. Zero knowledge is no extra knowledge other than what you want to reveal. So there's the state, you show A6 is water, and that's everything else. And for the entire proof, mathematicians say, gives you no extra knowledge, gives you zero knowledge. I don't know, I always find that name confusing, but like, that is the precise meaning of the term.
Yeah. Nice example, governance, a couple of months ago, years even, not really sure. Yeah, February 2023. In collaboration with Aragon, still built a proof of concept for private voting. So basically you say, hey, I have this NFT, I have this thing that, again, proves that I'm a member of a set, and I'm going to cast a vote privately for this. And the only thing that gets revealed is the total tally of the votes, and nothing else. Everything powered by zero knowledge and by virtue of the magic of Merkle trees and another small gadget that we'll see in a second that's called nullifiers to prevent duplicated votes. Sorry, wrong keyboard. Another interesting use case is provenance. There was a very, very nice project in Hackathon not too long ago called CK Microphone, in which people basically bundled the Raspberry to a microphone, so they would digitally sign audios that they were generating, so you could prove that that audio was just recorded with that particular phone. And the beautiful thing about this is that they then added serial knowledge on top of that for proving the correctness of any modifications they did to the audio. So for instance, if you need to bleep audio because you were saying something sensitive, you wanted to remove background noise or something, that's a transformation you do on the audio. But what they did is they ran that with a serial knowledge as well. So they proved that, hey, this resulting audio that I'm giving you comes from an original audio that I'm not giving you, because maybe it has sensor-sensitive information, that was recorded with that phone. And that's the nice thing, like you can apply transformations to media. This is also very much used in photography, like you crop a photo, for instance, or you make some adjustments to it, and you use serial knowledge to prove that, hey, like the original photo was actually digitally signed by this particular author. So you can